All righty then. Well, the thing says we're live, so we're live. Hey guys, what's going on? Yes, Kali. Yes. We're going to go through that. And actually, if you I have no idea if you're free or not. Hold on. We're gonna send Kali a quick invitation on the Twitter, just in case if she happens to be free, because we're kind of talking about her wheelhouse right here. So let's see. Hey, God, so many stuff and things. All right, so we'll drop a link there if you are free. There we go. All right, a link has been dropped. Okay, so we got that there. Oh yeah, Kali, there's a link in the doobly-doo down to your channel as well. So we're gonna pick up where we left off on Friday. Where the heck did we leave off on Friday? So let's do a little inception here. Why? Rather than just summarizing, let's just go back to what we did. Okay. I didn't come out with the video because I was a terrible person. Let's see. All right, so we are where was it? Oh no, it was a live stream. I know, such terrible. Okay, it was called It Would Be Light. Okay. Okay. So we'll present here. Oh, is this how this works? Oh, it's got a new little tab here. All right, let's see. Now let's just share screen, this tab. All right, so if we let there be light, everybody. All right, let's do a little inception back to Friday memes.
You'd have this wormhole that would go through, but it's twisting around with a Mobius
Oh, the
twist,
wind
a
grin.
figure eight structure there, and sucking all this light into it, condensing it down to, according to Thad's calculation, about the charge radius of a neutron. And it's twisting around, twisting around. Are we effectively finding a smooth way to square light, my friends? That's what I'm conjecturing here.
I've heard other people say
We're
similar
basically out
things.
of time. Um, now, again, that's a crazy thing to say, and it's like I've said those words, and it's like, how does that even work? It's like, and then I made excuses. I'm like, all right, well, I don't have all that fancy. Flat has some fluid dynamics software that's really expensive, but it's on an old laptop, so it's like, and those licenses are really expensive. So it's like, oh, I don't have the software. Boo hoo me. I'll wait for someone else to do some calculations. I did some calculations. I assume that if there was something to the words coming out of my mouth, and again, these are just rough calculations going through, you're going to need to do with all the other hydrodynamics and stuff like that, or whatever fluidic dynamics we see to use hydro and fluid very fluidly, interchangeably, which is interesting. But I did some calculations. Again, they're probably wrong.
Welcome, Blug.
I still need to make my mistake, but even if it is a mistake, it's a thing. Occasionally, you find something where you're like,
Top
I
five
expect
craziest
this to kind of be
calculations.
close, but this, yeah, it's not going to be the same. And it wasn't the same. The factor that popped out was very fascinating. So, Neutron Decay Cosmology for the win? No, I guess we're going to have to see, my friends.
All right, that's the point where we're basically at before we signed off. Uh yes, welcome, Lug, Grizz, and Kali. Kali, I shot you a link over there on I think the Twitter. So in case you're available, I have no idea what you're up to. The situation there, it's like, oh, somebody's online. They're obviously available. Oh, people could be working, doing this, babysitting, doing this or that. People are complicated creatures. That's why I play on Wolfram Alpha because it seems far easier. Um, all right. So that aside, what are we talking about? All right. So now to actually summarize after I gave myself a few minutes to warm up playing things that randomly came out of my mouth before. All right. So basically, we conjectured before. If you grant me a spherical cow and at least a particular field configuration where we're using basically the hyperbolic figure eight, not in particular its complement. Why? Because it's a little toroidal donut with a little figure eight in the center there. It's pretty cute. But the claim is if we have a particular field configuration, utilizing that as the primary, let's say, mover, so to speak. Why? I'm going to explain. The claim is that object, really small, like 10 to the minus 8 meters or something like that. All right. It's got this rotation going in on it. All right. It's got rotation, but since it's also got that little vortex that's going through a particular configuration, by its nature, it seems like it's going to suck things up. It's going to get squished down to about 10 to the minus 18 meters, roughly about the magnitude of the Planck charge, which coincidentally happens to be around the charge radius of like a neutron or proton, right around in there, because we don't really know exactly what it is. And I'm like, okay, now we've added something. Now, if you're going to add something to whatever the prevalent model is at the time, you're adding an epicycle, or so to speak, there. Okay. How does that make things simpler? Okay. The claim, and again, this might totally not be the case. You could probably use this similar configuration and do your standard. All right, we got matter, we got antimatter, bada boom, bada bing, baryogenesis, baryonic acoustic oscillations, annihilation, this, that. Okay, maybe that is totally the case. Or if you grant us this field configuration and we start at a very hot, dense state, roughly a little bigger than an electron, but it's essentially got a Planck density of mass energy. The Planck density is mass divided by meters cubed. So you get a mass and a volume. Okay. If you do the whole MC squared thing and you take that mass, you multiply it by C squared, at that point you get the Planck pressure. Under pressure. Thank you, Dr. Ossenfelder. That meme is stuck in my head. All right. But essentially the claim is, all right, what happens if rather than we got our matters, we've got our antimatters, they're going to annihilate. What happens when they annihilate? We get pure energy, i.e. photons. Okay. So my thought was, we got all these different particles that have their own antiparticles and cancel out. It's what particle is its own antiparticle? The photon. So the claim was, if we have a particular field configuration in a very hot, dense state, and we let there be light, we have our field configuration, we have light, energy, whatever the heck that might be. And you get this little vortex that's sucking things up, and it's going careening around a loop, going all the way around another loop, and it's being twisted Mobiusly. Light can't go. That's what the light cone's whole like 90-degree angle. So if you were attempting to, let's say, bind light in some form of, to us, a spherical style configuration, you're gonna have to have it crunched down going through some ridiculous system that, as far as we know, we do not have the ability to actually replicate. And if there was a way to be able to take light and form it into a form of matter, what better way to do it than perhaps conjecture, the primal element that's literally cinching reality together? That's ultimately the claim there. But welcome, K-Shell. Let's see, where are we now? Yes, memology, yes. 105.FM. Have I listened to that? It used to be 107.3 was the local rock station. WAAF rocks. Caleigh is commenting that's why maximal each flow is 90 degrees to the other. Well, see, what I'm thinking is if you got a whole bunch of photons, just energy, it's being condensed down, and it's all the while it's undergoing a Mobius twist there. So it's being twisted while it's careening, being condensed down, going around a loop.
continue twisting, going around another loop, comes right out the other side. I'm just thinking the simplest way to do it is, well, what gives you all the components that we really need in the universe, so to speak? I'm like, well, I mean, you got a neutron, because if you just happen to have a free neutron, it's going around and give it about, I don't know, like 15 and a half minutes, going to decay to a proton, an electron, a photon, an anti-neutrino. It's like, all right. So we seem to have the building blocks there. And then as things are going along, the problem that you run into, but the hydrogen, I mean, you got protons and the electron. Oh, the other things, well, it's probably going to, maybe you could still get see, that's where the heavy duty supercomputer hydrodynamic software, because now it's like, all right, you're gonna have to truncate your model at some point, because if you're trying to account for everything, the only way you can kind of really do that is if you're actually doing the system itself. And since you don't really have a computer the size of the universe, except for potentially universe, we got to make some estimations here to try to model things out. Okay, so I don't have all that software and everything, but I'm like, all right, let's do that whole spherical cow assumption. The whole thing within physics, when somebody uses the term spherical cow, what the heck, you're like, what the heck are you talking about? There's no such thing as a spherical cow. That's the point. The point is, it is an idealized situation in order for us to maybe take a look and try to figure out what may be going on here. Yes. Welcome, Charlie. I think you're going to like this. Caleigh's saying that a neutral creates a certain local gravity density to stay a That's very interesting. I mean, that kind of seems to be what it does, but I can't say. I'm not a nuclear chemist. But I'm gonna do it on the internet, and we got Wolfram Alpha. So let's follow through the logic. And again, I'm sure there's a mistake here somewhere. But I did some basic calculations. And again, this is within the top 5 calculations of WTF, mate. I'm not going to be as bold to say this is number 1, because again, there's probably some error here that I'm missing. But oh, don't worry. We're getting to the good part right now, Nolan. It's yes. It's all right, Charlie. I see you. It's okay. It's always, I was talking with Charlie a little bit the other day after the Demystify Sci folks. We were chatting a bit on Discord with some folks. All right, so let's actually get into what the heck we're talking about. So what we're talking about, okay, let's start here. So we're gonna actually, let's do it on the board. So I'm gonna put some things on the board, and then we're gonna go through a Wolfram Alpha. So feel free to trust, but verify. Because again, it's like you're doing a thing and there's a very obvious mistake. It's like sometimes, like if you're around somebody or if you're in a class or something, you got like a professor. It's like professors are like really smart and they know lots of stuff, but even professors make a mistake. It's like you're a student, you're like, I can't correct the professor. It's like, but if it's so obvious, it's, I don't know, do we get into the emperor is wearing no clothes situation? It's like, oh, that's a splendid fabric there, sir, and everything. You got around kid on the street, it's like, mommy, why is boss man like naked over there? And you're like, don't say anything. It's like, why? I see. I thought we learned about all these cults of personalities and stuff like that before, but I don't know. Emotions are difficult. So let's do this. All right. So we're going to make a claim here. We're going to make the claim of the massive universe. I know. We're committing blasphemy right off the bat. All right. So when I say universe, it's saying small u, because if we're going to propose a limit of space, or at least a radius, that leads to the following question philosophically. It's like, well, what's out there? I don't know. Darby dragons? Some folks say, well, that's not a good answer. It's like, I don't know. Maybe this is why people like the infinitesimal. So it's like, all right, we're dividing by 0 because we keep on getting smaller and smaller and smaller. Because if you keep on getting smaller and smaller and smaller, then if you're going to do maximum extendability, we can get infinitely small, then we should be able to get infinitely big, right? Something like that. I mean, okay, but if you had a limit that maybe popped up from calculations that we've known about for a while, like the Planck length, it's 10 to the minus 35 meters, very small thing. Well, let's do that over here. I'm gonna have it be L sub P. That's the Planck length. Okay. So what we're gonna do is that is our essential unit, Planck base unit of length. Okay. We're gonna divide it into its reference. Now, the Planck length is in units of meters. So we're going to take the one, and we're going to divide it into the reference one. We're going to put it into meters. Okay. So what we're going to do is throw brackets on this. We square it. Okay. Now, the claim is that this is going to be equal to m sub u mass, or more effectively, something along the lines of the mass bank of the universe. And then we're going to have some field configuration that this is going to be operating on top, at least to the best of my knowledge and from what I can see that seems to be going on based upon at least the calculations. So we're going to take another Planck unit. So this is the one of length. I'm going to take the one of mass. So we're going to do m sub p for the Planck mass. Okay. And the claim is when you do this, you're going to get out the magnitude of the inverse Planck length squared. So you're going to get the inverse of the Planck area in meters. So it's like 10 to the 69, some ginormous number. And the claim is, since we've got a length divided by a length, you got a mass divided by a mass, it's going to give you a dimensionless number. And that's essentially the connecting factor. The whole claim that this will lead to the mass of the universe. So we're going to say m sub u. That's going to be approximately, just for reference, 8.3315 times 10 to the 61 kilograms. Ginormous number, ridiculously ginormous number. Okay. Now you get that number and you're like, so what? You just said some words. Means I need more evidence. You need more of a case. I totally agree. Yeah, you see a ginormous number. It's okay. We'll do the little thingy right here so everybody can see it. See where we are. Okay. So do this guy. All right, show the class. Boom, boom. Let's share this guy. All right, so window. Boom. Okay. I'm gonna do exactly what we are, except since we don't have that number, what we're going to do is we're going to do the same thing. We're going to solve for x. And we're going to put our dimension in kilograms because we want to get that dimensionless number. We're going to put out the Planck mass. That's also in kilograms. So that's will give us a dimensionless number. I'm going to set it equal to, we had meters. We divide by the Planck length. Okay. And we're going to square that all. Why? Because we love squaring things in science. It seems to be very useful. Okay. So what we got here? We're solving for a mass in kilograms. And we have it set up as we have the reference of mass, kilograms. We have the one of kilograms, the Planck mass. We have the one of meters, the meter, or the one of length, the meter, versus, the reference of length, the meter. See, I messed that up already. Divided by the one of length, or the elementary length, the Planck length. That's all squared. We hit enter. Okay. Now, Wolfram Alpha does the hard part for us. See, this is essentially that dimensionless number. So basically, If you did 1 over the Planck length squared of the Planck area, you're going to get this. So instead of 10 to the minus 70 something meters, you're going to get this number here. Okay. Yeah, that's this freaking ginormous number, all those numbers. Okay. So what the heck is that number? Okay, I don't know. I'm just going to slap kilograms on it so it will tell me. So you see the 8.331, that's going to round up to a 2, but I'd like the extra accuracy there. So it's got that many kilograms. Grams, that's 1,000 grams per kilogram, literally by definition. So we're going to lower it by 3 orders of magnitude. So we're going to do this. For sake of argument, we're going to move that 61 kilograms, make sure it's same thing. Okay. So let's take out the x just so it doesn't get confused. Put times that. Everybody make sure it comes out to be the same number. So, okay, same thing. All right. So the claim is this is essentially mass bank of universe, so to speak. Okay. Why? It's well, this is the thing, Caleigh. For many of the things you say, I'm like 80-something% there. It makes a lot of sense. You start talking about Bernoulli. Let me look into these Bernoullis. I'm like, oh, this is very interesting because you never know where a good idea comes from. So let's see. All right. So we got that number. What is the significance of this number? Okay. So I'm going to present my evidence very quickly because we've gone over this a little bit before. Why might this number be interesting? Okay. So we take this number, we do c squared. Okay. Given this big number, a bigger number, it's something 10 to the 78 joules because we just did a mass times c squared. So we get our E equals mc squared conversion to energy. Big number there. Okay. Why is that important at all? All right. Because coincidentally, that's mass energy. Okay. So if you combine different terms, you're going to get different units, constants, dimensions of measure, so to speak, as we have basically set up for physics as to best describe things. Okay. So there's a thing called the spring constant. So if it happens to have the dimensions of mass, so we'll do like mass, and that's over time squared. So we'll do Planck time squared. So this is essentially the Planck spring constant. I had never heard about it. It's actually not even on Wolfram Alpha. You actually have to put in these dimensions, and it'll tell you what it is. Okay. So as we can see, that mass divided by time, so that we have the negative exponent in there in this form. It's interpretation of the spring constant. Wait a second. 10 to the 78. That number looks highly familiar. Very interesting. Let's steal this guy. 7.488 times 10 to the 78. 7.488 times 10 to the 78. Well, that's interesting. Okay. And then note the dimensions are different. This is energy. That was a spring constant. Okay. So what happens if you took this conjectured mass energy bank of the universe and you divide it by the Planck spring constant? Oh, look, we get 1 meter squared. That's very interesting. We're getting our reference of length squared. I think that's neat, but I think the easier argument, again, we're still at the point where I'm trying to present a basic case to justify this number that I'm using here. Okay. You don't have to believe it. I'm just making an argument. Okay. So if you happen to take this and let's say you divide it by, I don't know, the Planck density. Maximum of density. It's like 10 to the 96. Okay. You take this, you divide it by the Planck mass density. 1.616 times 10 to the minus 30. Wait a second. This number looks suspiciously familiar. 10 to the minus 35. That looks suspiciously like the Planck length.
Huh. So coincidentally, if we take this number and hypothetically, we ju- just for this and giggles, divided by 1 meter squared. Because that was the last thing that popped up. Oh, wait, sorry. I meant multiply. My bad. Wrong side, wrong dimensions. Noob. Why am I confusing myself? Okay, so let's just do this. Let's just divide it by the Planck length. Actually, no, let's just do what I know before I dig a hole any further. All right, you got this here. Okay. Meters squared. Let's just do that. Okay. Never mind. Is this equal to the Planck length times meters squared? Oh, we don't way to leave us hanging. Not going to give me an answer, is it? Okay, so long story short, we just do that. Planck length times that gives us the same dimension, cubic meters. It's almost like I should practice through this if I'm going to attempt to do a presentation rather than, hey, the the beautiful thing about live internet. Yes. Let's see. Oh, we've got a goldfish joining us. Ooh. Ooh, the Planck length and rats. Well, I was born in the year of the rat. The claim is give there be more rats than Planck lengths than we observe. Um, that's I don't know if that's biologically possible. Um, I don't think that's the case. And again, I'm not a biologist or anything. That's Dr. Michael Levin. So super universe. Listen, some of these other dimensions and everything, you run across things that you had no idea and everything. A lot of these things are particular to individuals in particular fields. Like you'll have some dimensions, and there's like 60 or 70 different interpretations. It's like luminous intensity, the dimensions also is like the dimension of crabs. Like, yes, like it's literally a dimension of, hold on, crabs. Yes, crabs is a unit, my friends. Crab. Oh. Oh, look, 42 crabs or 10, oh, 10 to 7 crab. What is this? It is frequency integrated spectral irradiance with respect to frequency. I have no idea what that means. Welcome, Rick. I'm just messing up on some very elementary calculations that I haven't practiced before, but good to see you. All right, so we'll get into, yes, but basically that's mass divided by time to the third. Okay. All right. So I'm essentially making my case about why, if we happen to use this particular number for the quote unquote, let's say mass bank, so to speak, because we convert it and stuff like that. All right. It's kind of a reservoir, if you would. Okay. It's also about 10 to the 8 times the ordinary matter in the universe. So it's going to be a recurring theme because ultimately the claim, at least I'm postulating, is if we happen to have a minimum length and we invoke maximum extendability, you should have a maximum to that. And if they would be the inverse of that to its maximum within its units of reference, you're going to have a maximum radius, so to speak, if there happen to be a minimum radius. Ultimately, most of these come down to about 10, basically 100 million times larger than the stuff and things that within our observable universe. That's ultimately the claim. And again, could be totally wrong. But we're going to continue now. All right, so let's get into the calculations. So hypothetically, if we happen to have a system that had a method to generate, let's say, we're just going to say the particle stuff and things that we see within our universe, so to speak. Again, small u universe because it's, my God, no profit or anything. But
if we happen to have, let's say, and again, feel free to have your matter, your antimatter, your annihilation, your baryonic acoustic oscillation. I'm totally all right with that, whatever. Now, hypothetically, if you happen to have something, a particular geometric field configuration, so to speak, and you had something that had some rotation, and it's going to add a bit of a rotation gradient to all this very hot, dense state, and it had a little vortex in it that happens to be undergoing a Mobius twist, looping around not once but twice, going through its full figure eight and going out the other side. Hypothetically, if we start off with, rather than all the particles, because I'm looking through them and I'm like, yeah, but how do we do that or that? And it's like, then you get to like the photon or whatever a photon might be, light. If we let there be light, might we be able to account for what's going on? Because I did add in a complication. I'm saying there's a geometric field configuration, blah, blah, blah. I've added in an epicycle. I better take away, or at least posit some way to help explain more with less. Because if you're going to add something more, maybe you need to explain even more. So we don't necessarily need other things. So hypothetically, if we had that 10 to the 61 kilograms right here in mass energy, okay, so we would have like 10 to the 78 joules or whatever, and we're right around the size of an electron, and we press start, and we're going to have C expanding. I'm not going to say expansion. You can invoke it if you want. If that's useful for your model, please, by all means, use this stuff. I'm not sure it's necessary. I didn't use it for these calculations, and we're just going to go through real quick, and I'm going to lay it out step by step and see what you all think. Okay. So if we take this and we were to follow Caleigh's proposition, as she had stated, that what happens if you were to go to a super dense point, and let's say you got a neutron. I know, right? I know, right? Because also at least according to Thad's calculations, the vortex of that knot is getting down to about 10 to the minus 18 or so, which happens to coincide with our theoretical thoughts of the radius of a neutron or proton. We're still not quite sure. I think for its charge radius, could be wrong. Proton charge radius is a bit different, I believe. Don't hold me to that. I usually trust but verify. But essentially, the claim is you're going to take all this hot, dense energy, and you're going to swirl it around. It's going to loop around while Mobius twisting once, and then going around again, and then going out the other side. What happens if, let's entertain the idea, what if we just start popping out all those neutrons? They start decaying around. We're getting our protons, electrons, antineutrinos, some photons and stuff in there. And that's going to happen. How the heck long would that take? Would it line up with anything that actually makes sense? Okay. So here's what we do. We do the obvious thing. We take the claimed mass bank of universe and we divide it by the mass of a neutron. How many neutrons do we need? About 10 to the 88 neutrons. That is a very big number, my friends. That's going to take a while to get there. Okay. So here's the thing. These are the original calculations I saved. So what I was doing is Rick, who's in the chat right now, has been a big proponent about maybe if you look at things inversely, perhaps something like the Newtonian gravitational constant. If you end up with terms that you start seeing frequency or frequency squared, that's an interesting thing. Because if for each tick Planck time, the inverse would be the Planck frequency, right? Okay. And at least, and again, I'm not a quantum mechanic, I'm not a quantum field theorist, but you hear all this stuff about quantum field theory. What are particles? Particles are oscillations. within the particular neutron field, proton field, or whatever elementary particle field. I realize those things that aren't technically elementary particles. So there's vibrations and fields, and we've got all these different fields and stuff. I'm like, okay. So do they all need to be separate fields? Because technically the Planck frequency is a maximal frequency. Because once you get to the Planck frequency, I think you divide that by like 2 pi and you get like, I don't know, Planck mass or something like that. So that's very interesting. I mean, since we don't really have any Planck mass, so to speak, particles that at least that we have observed or something like that, we seem to have a spread of different things. Could we allocate that within the frequency bandwidth? Again, I'm not a radar tech or anything like that, but I'm just asking a question. So essentially what I did is I took the Planck frequency, and then this is the quantum frequency of the electron. So basically, let's take that out. So I'm just figuring how many electrons you could fit within the Planck frequency, and then just tick the clock along. Okay. So about 940 mega electron volts, blah, blah, blah. So that's roughly about, a little over the mass energy of a proton, i.e. a neutron. Okay. All right. So we take this number. It gives us this. This is essentially our conversion rate, our claim conversion rate of if every tick of the clock, so to speak, we could convert 1 Planck mass of energy. We could convert 1 Planck mass energy equivalent of energy into mass. And within the Planck mass, you would essentially get this many neutrons out. Okay. So we're gonna, I know the blasphemy is rife tonight. Let's see what else folks are saying. I'm sorry. I often miss things, and when I go back, I get confused. Let's see, Charlie is saying that, what is this? Charlie is saying that if a particle existence is emergent, the statement would be true. You could backtrack there and find yourself at the Taurus. Okay, I believe you mean Taurus. Don't get me wrong. I am actually a bull Taurus until they redid that astrology thingy where now, I don't know, am I Aries or something, but I identify as Taurus still, and might explain a lot. It's technically TORUS. I still misspell things all the time. Don't worry, man. All right, so Caleigh is saying that it can't be a torus because a torus has 2 sides. And that would mean that matter and antimatter would be eternally separate. Yeah. It's almost like maybe we got like 2 spheres of influence and never shall the 2 meet. Again, I'm still working through that. I mean, to be fair, Thad has been saying that for a while. And that's still one of the things I'm working on. Like, if you do the 4-dimensional hypersphere, okay, let's just do this. All right. Go over to our friend, the hypersphere. Okay. So we do a make sure it's in the right dimensions. Okay. So if we're assuming quote unquote S3, which is what? It's a 4-dimensional sphere. Why? Because we're going by surfaces. So it has a 3-dimension, basically our standard ball in our 3 dimensions. You get a basketball, assuming it was smooth, it's basically quote unquote S2. So basically, whatever you feel it is, subtract 1 because we're talking about surfaces. Okay. So we got our 10 to the 69 number there. That's the Planck inverse of the Planck length squared. Okay. So long story short, let's get the number that makes sense. Okay. So essentially, content. We're basically dealing with at least 2 spheres that are offset by this 4th dimensional thing here, that 10 to the 39 thing. Okay. All these dimensions right here. So hypersurface area is in 3 dimensions. So one of the problems I run into, and one of the reasons I like talking to smarter folks than myself, is how the heck do I grok this? What the heck does this even mean? To be fair, this is all just based upon the radius, which that's just the inverse. That's that whole meter squared over Planck length. I just put in like, I don't know, 40 something digits for this calculation, just because hypothetically I could. Uh, so basically, the universe as we know it is about 10 to the 26 meters, according to our observable universe. This is about 100 million times larger. Okay. So the only thing is you're taking that for your radius and you have it raised to this particular dimension. So the only difference between this and this is raised to a higher dimension, and it's like a difference of 2 pi squared, I think. That's just kind of how it goes. That's a nitty-gritty detail. But I don't know. Where do we live? Do we live it if because it's easy to justify this? I'm like, well, technically, if that whole Mikowski space, yada yada. Basically, if you can use four-dimensional math using lengths, and we can just change a signature and then make a one minus, and it's like, all right, well, that's our time metric, and then we can grok out everything. It's like, okay, I can tell a story for that. Now, the question is, how does the field configuration set up? Is it just sitting there? Because there is also interesting geometry that I believe exists. I've at least seen some pictures. I believe something exists where, well, what if hypothetically you took this 3 dimensions that we know and love? What if, I don't know, time as we experience it was just the inexecuable, oh, how is it? Time is simply the inexecuable continuation of computation. So literally just as we progress, that's essentially, we're literally just going through this 3D thing, and as we progress, a tick tock goes on the clock. I don't know. See, that's my personal existential crisis. Uh, that aside, I try to go through, see how much I can try to figure out, get an idea, talk to other folks about different ideas, and all of a sudden somebody says something, and you're like, oh my god, that might not be even relevant, but that comment like jingled some neurons or something. So things seem to make sense. Um, Now, for where we live, that might be an interesting thing. And again, I have no idea. It's like what Caleigh is, that whole single-sided surface. It does seem to make a lot of sense. I'm just kind of taking what a lot of other folks have said, using a lot of this, and coming to some. Let's. Oh God, we're already 42 minutes in. Inexorable. Yes. Thank you, Rick. Yes. Inexorable continuation of computation. Wow. I could not say it. See, the problem is that sounds like a hard word, and I think I've actually said it correctly far too often that I'm like, wow, I'm surprised I didn't screw that up. Well, of course I screw it up now. When was be wary, Charlie, when you use the term isomorphic. Mathematicians might have a field day with you. Basically, you're saying similar, and you know what? Maybe that is fine. It's just you start talking with some different folks, and you go on some of those different math boards, and then you see mathematicians. It's like one of the greatest compliments I had was that when I think either Shiloh or Anastasio on Paradigm Drift was like, "Yes, we have our first mathematician or something here." I'm like, I ain't no mathematician. I mean, those are beautiful words, and I mean that's a great compliment. Personally, I hold mathematicians in high regard. Uh, yes, Ray. Hey, I'm on the East Coast, so it's irregardless here all the way long. But what about regardless? Uh, oh, that's fine. No, see, this is why we get along because it's like, well, when I had you on and stuff, you're like, I can stretch your crazy things all the time. It's like I do that too, and then all of a sudden, it's like, okay, I'm not going to stop conjecturing crazy things, but certain things that I actually am gaining confidence in, I'm going to be a little bit more careful with, because even was when we were sharing the clip from Skydive Phil Harper, he had the gentleman who I had first learned about maximum extendability from, and they're even saying, listen, a lot of times you go on a talk, you're just kind of like shooting back in the air, just kind of like just chatting back and forth and stuff like that. You're a bit more casual. you say something, someone's like, look what you said at like 2 hours and 17 minutes or something in this interview from like 13 years ago. It's like, yeah, maybe I misspoke or something. And then even on, what is it? One of those Professor Sean Carroll's with Dr. Cesarati. Um, I think she was talking about the inverse or something about the relationship between the Planck mass and the Higgs boson. And she was like off by like an order like magnitude. But if you're looking at it in a particular way and then you invert it, it's it's an easy thing to mess up. I knew what she was saying, and well, I knew because I literally have the calculations right in front of me at the time. So it's like I understood what she was saying, and then it's like, oh, is this an issue? It just seems to be set to the magnitude of the elementary unit of action, but I mean, hey, what do I know? Uh, okay. Well, see, one of the things that gets me is a lot of folks, at least what I noticed, there seems to be that whole meme within the greater physics community. And I say this as somebody that's an outsider, um, of, oh, everybody, please be quiet. A retired engineer is speaking. And like, you get a lot of hate on and I'm like, well, to be fair, I'm like, if you're an engineer, like your job was to build things. So why wouldn't I listen to an engine? And again, like I think it's the meme that you'll have somebody that looks at something and like, well, it's obviously this, but then people don't say anything. It's like, well, somebody tried this years ago and then that didn't work or something like that. So it's I don't know. I don't know. And personally, if you're an experimentalist, I'm like, aren't you kind of an engineer? Like, aren't you engineering the devices that have like precision that just makes the mind wobble? Yes, I used the Kelly Bundy quote right there. Okay. Okay, let's get to the punchline now that we're almost over. All right, so we'll close out of this. Okay. So quick summary. All right. So the claim is we have this ginormous number as the quote unquote mass bank for universe. And we have some process, we're conjecturing, that could take that mass energy, convert it into something that we know and love. The neutron. Okay, to be fair, none of us really know neutrons, but we consume neutrons because it's some of the building blocks that is very useful to us. Cool. All right. So if we take this mass and we divide it by the mass of a neutron, we're going to need this many neutrons to account for the stuff that's going on. All right. How do we do this? So how I originally do this, you took the Planck frequency. So within the Planck frequency, you take the Compton frequency of the electron. So we should be able to create this many neutrons. All right. 10 to the 19 neutrons per tick of the clock. All right. We continue. All right. So then what I did was, okay, how did we do this? Oh, I think I was like double checking. Yeah, the mass of okay, because this is the same number. Okay. I do something convoluted and there's another way we can oh, did I just lag? Oh, lagged. Okay. So ultimately, yes, we get this redonkulous equation. All right. So we get mass of universe, so to speak, or mass bank, divided by the neutron mass. That'll give us that 10 to the 88 number. Now, let me actually go through. What was this? This is a crazy calculation right here. All right. So that'll give us the 10 to the 88. So that's the number of neutrons we need. And then I'm taking the Planck frequency. Okay. So we're taking a tick of the clock and how much frequency. Oh, that's where the Planck's constant comes from. Okay, because that converts it to the wavelength. So that's that many. Okay, so we need that many neutrons. We can get this many neutrons per tick of the clock. And then for some reason, I just divide by the Planck frequency again. But what you can do is, okay, you just multiply it by the Planck time. Because otherwise you see so many frequencies in there. Oh, you're like, oh my God. Okay, so that should give us the same number. All right. So we had 10 to the 25 seconds. Let's just verify. All right, 10 to the 25 seconds. All right. What the heck does that mean? Okay. So the claim is it's about 10 to the, okay. It's about 100 million times more time than we believe has occurred within universe, or at least within the standard paradigm. Because right now we believe the universe generally accepts it's about 13.8 billion years. Billion is 9 zeros. So since we got a 10 billion, that's 10 zeros. Okay, so that's 10 to the 10. This is 10 to the 8. So basically, about 100 million times as old. Oh, that seems to be about equivalent to about that. What is it? That 100, yeah, about 100 million times more mass of the observable universe. All right, see, anytime we see that, that makes me a little happy. Why? Because that also means if there happen to be some inherent curvature at some point, we should be able to measure that, hopefully. There might be a good reason we can't, but ultimately, maybe this is why things look flat. Why? It's freaking ginormous. Okay. I haven't gotten to the punchline yet. Golly, you're still here watching in the future. I think you're going to like this part. Okay. So let's go back over here. All right. So we got up here. So we got to this crazy unit, this ginormous 100 million. It's going to take longer than we believe the universe has existed. Okay. That's a problem. Only if the universe has only been around for about 14 billion years. Here's where I start having some major deviation. And again, I could be completely out there. I know Professor Gupta, uh, he had written a paper that Joe Rogan had shared, got a lot of attention, claiming that universe was closer to about 27 billion years old. Why? It's like, well, it's galactic formation. It's like, hey, he's introducing some changing constants, their tired light a little bit. He's doing a little things there. Now, you can disagree with him. A lot of people do. But at least according to Professor Keating, it's like, listen, he at least provided the scientific explanation. And you can disagree. That's fine. You put in the work, you present your case, and then people can judge it. And then as the experiment goes, if people are like, you know what, maybe that's something there. My thing is, I personally think the universe, as we know it, it's probably a little older than 14 billion years, maybe a lot. Okay, so the punchline. What? Why are you saying this? Why would you make this crazy claim? This doesn't seem to line up, except if universe with a number of magnitudes is about 100 million times greater in, like, I don't know, time, maybe space, maybe mass or stuff like that. Okay, or at least it with accumulation. Basically, the ultimate magnitude will be larger, but a lot of it seems kind of the same. All right. So we got this time. Now, the claim is, all right, how much time would it take? So hypothetically, we took this to this number right here. All right. So this is the number we actually have on the board. We'll bring this down. So it's that whole thing. I know it's a little shiny there. You get that little light pointing it, but this is basically this term right here. Oh, that's actually a little different. This is meters divided by Planck length squared. This squared is on the outside because it's giving us a dimensionless number for this squared. This is different. What we did is we have meters squared divided by Planck length. Why? Meters is our reference of 1 for the dimension of length. Basically, we want the inverse of the Planck length in the dimensions of meters. So this is low-key how you do it, because if you take that, you're going to get that 10 to the 34 meters, which was that ginormous number we saw for the hypersphere. Okay, that's all that it is. It's just the inverse of the Planck length in the units of meters. Okay, so what did I have here? All right, so the claim is if you start, and again, assuming we start at the size of the electron, grant me a spherical cow. I'm not accounting for that little bit there. Why? Because light is fast. So the claim is, how long would it take for universe, so to speak, to reach from a minimum to a maximum extendability? So I think I have this wrong. It should be, is it oh no, divide, if I multiply by c, that should give me, I think, a length. This will give me a time. So basically, if you take that and you divide it by c, it's going to give you out a unit of time. Okay. So basically, it gives us out this number here, which is different than our previous number. That's 10 to the 26. This 10 to the 25. Okay. But they're about 10 to the 18 years. So about 100 million times longer than what we believe current age of universe is. I know. This is where we're committing some real blasphemy here, friends. Buckle up. All right. So I see this number. I'm like, okay, I didn't expect the numbers to be the same. That would just kind of be weird there. The relationship I found is a little bit weirder. Okay. So this is the calculation for how long it would take, hypothetically, under idealized circumstances, to produce this many neutrons from the quote unquote mass bank of the universe. Okay. It's going to take a redonkulous amount of years, but how long would it take for universe, so to speak, to get to a maximum radius? Well, obviously, even longer, a little bit longer there. All right. Now, riddle me this. Welcome, Antoine. Good to see you. You're getting here for the end of the show, but it's a good time because we're getting to the punchline. So, if we take this calculation, and again, it's a spherical calculation about how long it would take to make enough neutrons to go through the mass bank of universe. It's going to take about this long. Don't worry about it. Big number. How long would it take from a minimal radius, assuming 0 rather than 10 to the minus 12 meters, because that's when a spherical cow, grant me a spherical cow, we're looking for a first level approximation. All right. So if we're going to extend at the speed of light, how long would it take to get to that 10 to the 34 meter radius, which is the inverse of Planck length within the units of meters? It's going to take this long. Big, ginormous number. Don't worry about it. Why am I saying don't worry about it? Well, the punchline is you take these numbers. Where is it? I think it's, where are we? Oh, I guess I'm just going to have to do it because that's another one. Okay. So here's what we do. We click on the thingy. All right. It gave us that many seconds. So we're going to take this. We'll throw it on the tab over here. I'm just going to throw our protective brackets on it. All right. Then we're going to go back. I'll take our other number here. I know, so ill prepared. This is what happens with a professional YouTuber. All right, we'll go back. We'll go over here. That one looked a bigger, so we'll divide that. The time it would take, conjectured, for light basically to expand into maximum form. Okay. So they're about a magnitude off, but they're kind of close enough. So here's the thing. What do we get? Let's look at the ratio. All right. We got this giant number divided by this giant number. What do we get? That's kind of weird. 6.283. The number looks familiar. Where have I seen it before? Let's click. Oh. 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 And that, my friends, is why this is of the top 5 WTF moments I've gotten for calculations. I'm not sure what to make of this. We just got 2 pi out of a calculation. One, trying to figure out how long would it take to generate mass given neutrons and stuff like that, production, versus how long would it take for light to travel to a maximum extendable radius. The ratio between those is a circle. I don't know what to make of that. Now I'm sure there was something in there with like I included Planck's constant to try to figure out the Compton frequency and stuff like that. But I'm like, ultimately, if you just did that mass conversion of just Planck masses, I'm pretty sure it's gonna essentially be the same thing because we're just taking a Planck mass and then saying how many neutrons could we get. Um, well, Callie, that does seem to be correct. Anything that's circular, that's how far around the surface of anything. Uh, I mean that's a fantastical thing. It's like no, I mean if somebody's happy, I mean that's just one of those calculations. I look at that and I got that, and I was talking to Thad like the next day, and I'm like, he's sharing me these things about like what he found. I'm just like, dude, this is cool, and it's like oh, have you noticed anything interesting? And it's like certain things. It's like is it interesting enough to really spend time on? Because a lot of times I'm sure I made an error or something, sure, but it's like I went back around. It's like you do that calculation, I'm like, why is a circle here? I'm literally just taking the basic premise of neutron decay cosmology. Like, what happens? You're going to reach a point of maximum density, and then if you start plopping off neutrons everywhere, it's like now they may be coming out extremely fast in massive volumes because it's like, I don't know, 10 to the 19 particles per Planck second. So you're talking about, yeah, that's probably going to look like a very hot, dense state. Um, I mean, ultimately, is that what's going on? I don't know. I wasn't there. The map is not necessarily the territory. Now, as we get closer and closer to truth, to Robert Lawrence Kuhn, it's hopefully he's all right. I haven't seen him do anything really recently. Uh, but as we get closer to what's actually going on, we should be able to discover and learn new things. And the big thing is to be able to leverage those things in order to make humanity better and hopefully a multi-planet species. So just in case if anything goes wrong, maybe we could perpetuate through the cosmos. Whether that's a good thing or a bad thing, I can't say. Uh, but I just thought it was a really cool calculation. You go through and it's like one I expected. I don't know what I expected. I'm like, if it lined right up, I'd be a little hesitant because I'm like, it's a little off. But it's 2 pi, so I'm like, okay, maybe again there's a thing there, or is it does that implying that just we need to go around for a full circle, or and again, maybe even if there was something to that, that could just be a happy coincidence. I mean, a happy coincidence if there was something to it. I mean, it has more confirmed digits then at least my claim of the Higgs boson mass should be 125.37 GeV divided by c squared. Yeah, I mean to be fair, it actually has been measured at that, but it's one of those things. It's definitely in there in my top five of you do a calculation and you're like, that's weird. I've shared some others and hopefully we'll be able to share some more soon. But that's all I really got. Uh well, let's see that's the thing. That was what. Why should there be any relationship between these things? I was just trying to be like, all right, if we assume this, if at some point we get fancy software and people want to throw some money towards us, and we can start to model this, we at least have a rough linear estimate about what's actually going on. I know there's going to be a lot more there, and maybe that 2 pi actually is saying something that maybe I don't know. We need to go through a full rotation to be able to, because at some point, if you are going to be quote unquote spreading out, expanding, whatever term you want for that field configuration, we're going to be where at least I'll claim. Um, it's going to dilute, so you're not going to get the same rate there. So maybe you have a full cycle there. Again, I can't quite say, 19K, good to see you, my man. We're just rounding out. The moral of the story is basically we go through all these calculations, yada yada. Basically, we have a total mass that we claim as the mass bank of a universe. What maybe it's right, maybe it's wrong. We went through some of the mass, but the long story is you go through, and if we assume this Caleigh, who's in the chat here, it said, what happens if you just reach a point of maximum density universe, lower U universe, because I ain't God or prophet or anything, loops around, and the universe, quote unquote, just keeps on recycling. Um, basically what happens if you spin a whole lot of Newton. Long story short, in order to go through that process, it takes this long. If we were to go to another conjecture, which was the maximum, how long would it take for light to reach maximum extendability radius of universe? You get this number, and when you look at the relationship between those two numbers, we get a circle. Now, I don't know if it's right. I don't know if it's wrong. Is yeah. Here's the thing: 19 came in. There's been so many situations where people just make a basic arithmetic mistake and stuff like that. They could be the smartest person in the world, and you watch, it's like, oh, I just made an arithmetic error. Happened to all of us, but we're all human. I think I've thrown enough math at you all for a, where are we at? Monday evening. All right, it's about time to hit the old dusty trail and get back out to Utah to the monastery to do some interesting stuff and things. But hey, thank you all for joining, and for all those who may join temporally in the future. Let's hope 2025 is a year humanity can learn to thrive. I'm gonna bet. I'm willing to bet on us. I think most folks are good people, and good people can figure this stuff out. This requires a little work and a little bit of attention. So, peace out, everybody. Take care, y'all.